De-Moivre's theorem. De-Moivre's theorem. Yes. Now statement: if n is any positive integer, then r cos theta plus I sin theta whole power n equal r to the power n cos n theta plus I sin n theta. This is the statement. If n is any positive integer, then r cos theta plus I sin theta to the power n whole power n equal r to the power n times cos n times theta plus I sin n times theta. This is the statement of the De-Moivre's theorem. Now we have to prove. Firstly, yes, obviously when n equal to 1, then you can put 1 here, that is r cos theta plus I sin theta to the power 1 equal r to the power 1 cos 1 theta plus I sin 1 dot theta. That is obvious. That is obvious. And for n equal to 2, we have, because n is positive integer, so starting from 1, we have r cos theta plus I sin theta whole power 2 equal r square, then cos theta plus I sin theta whole square. We have to use this formula, yeah, its power is 2, or simply 2 theta plus I sin 2 theta also we can write. Okay, this whole square gives, simply instead of that directly you can write r square, and what is cos theta plus I sin theta whole square? We can write that is, yes, cos square theta plus 2I cos theta sin theta plus I square sin square theta equal, we have to follow the pattern, r square, then cos square theta plus I sin square theta, and real part and imaginary part we have to apply here. Yeah, so this is cos square theta, I square is -1 minus sin square theta plus I times 2 sin theta cos theta. We are verifying this, r square, then cos square theta minus sin square theta is cos 2 theta, plus I 2 sin theta cos theta is sin 2 theta. Here now you can see the pattern that n theta is 2 theta plus I sin n theta is I sin 2 theta. Then from these two conditions 1 and 2, we verified 1 and 2, thus the theorem is true for n equal to 1, n equal to 2. Now we prove the theorem by induction method. Then we have to suppose let the theorem is true for some positive integer k. It is true for 1, it is true for 2, then let's suppose it is true for some positive integers k, and by our assumption that what we obtain, r cos theta plus I sin theta whole power k equal r to the power k cos k theta plus I sin k theta. It is this, and then multiplying both sides by r cos theta plus I sin theta. Then if you multiply by this, then in left hand side it will be r cos theta plus I sin theta whole power k plus 1, yeah, equal in left side r k and r is r to the power k plus 1 times cos k theta plus I sin k theta times cos theta plus I sin theta. We obtain this result, or the product is this. then what can we do here? We can see r to the power k plus 1 times as we verified already, cos k theta plus I sin k theta times cos theta plus I sin, that z1 dot z2, the product is, what's the z, the product of z and z2 is, we have to add this theta. In case of production we have to add theta, in case of division we have to subtract the angle. That's why it can be written as cos k theta plus I sin k theta plus theta, that the product of two complex number. Yeah, now r to the power k plus 1 times this is cos k plus 1 times theta is common, k plus 1 plus I sin k plus 1 times theta. We obtain this. Now if we judge this, r cos theta plus I sin theta k plus 1 equal r to the power k plus 1 times cos n what, 1 n is k plus 1 theta plus I sin n theta, rn times cos n theta plus I n theta, which shows that the theorem is true for n equal to k plus 1 whenever it is true for n equal to k, but we know that it is true for n equal to 1 and n equal to 2. And if it is true for n equal to 1 and n equal to 2, if it is true for n equal to 2, then it is also true for n equal to 3. And following the similar process, we can conclude that the theorem is true for every positive integer n. Hence, the theorem is proved. Okay, in this way we can prove this theorem. This is not so complex part, and I will show you the shortcut method as well. Next shortcut method, it can be done by this process using Euler's formula. Yes, here if z equal r cos theta plus I sin theta, then z to the power n equal to what? Z dot z dot z dot z, that is n times n being positive integer, equal, this is r cos theta plus I sin theta times r cos theta plus I sin theta dot r cos theta plus I sin theta dot 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 r cos theta plus I sin theta. We can write this. Then you can express using Euler's form, that is r times ei theta times r times ei theta times r times ei theta dot 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 r times ei theta equal n, there are n r's, so r to the power n and e to the power I theta plus theta plus theta plus dot 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 plus theta. Then we can write r to the power n into e to the power I n theta, then it can be expressed as r to the power n times cos n theta plus I sin n theta. It can be expressed. Therefore what is z? Therefore r cos theta plus I sin theta whole power n, that is z is this, z to the power n is this, equal r to the power n times cos n theta plus I sin n theta. Hence prove. This is De-Moivre's theorem. We can prove in this shortcut way as well. Instruction is apply De-Moivre's theorem to compute. to compute. Okay, now the problem number 1, that is 2 cos 15 degree plus I sin 15 degree. This is small bracket whole power 6. Now the solution is, here what we have given, 2 times cos 15 degree plus I sin 15 degree whole power 6. Now using De-Moivre's theorem, using De-Moivre's De-Moivre's theorem, yes, what we can, 2 to the power 6 times cos 15 into 6 plus I sin 15 times 6. Then 2 to the power 6 is 64 times cos 15, that is cos 90 degree plus I sin 90 degree, equal 64 times cos 90 is 0 plus I into 1 equal 64I is the answer. Here we have applied De-Moivre's theorem to compute this problem. Now problem number 2. Problem number 2 is 1 plus I to the power 20. Now the solution is, here we have given 1 plus I to the power 20. Then directly we cannot apply because we need in polar form. This is not in polar form, that's why we have to change into polar form. So we have to suppose z equal 1 plus I equal x plus iy. Then just we have taken this part, x equal to 1 and y equal to also 1. R equal to, x square plus y square, is it 1 square plus 1 square is root 2. This is root 2, you can find. And tan theta equal y over x equal 1. 1 by 1 is 1. Therefore theta equal pi by 4. That means 45 degree. Now in polar form you can express z equal r cos theta plus I sin theta equal, what is r? Root 2 cos theta is cos pi by 4 plus I sin pi by 4. But what we have given, z to the power 20. So z to the power 20, as we have supposed this, equal root 2 times cos pi by 4 plus I sin pi by 4, or 45 degree also we can write, is whole power 20. Now using De-Moivre's theorem, using De-Moivre's theorem, what can we do? We can write root to the power 20 times cos 20 times pi by 4 plus I sin that 20 times pi by 4 equal root 2 is क्या, what, 2 to the power 1 by 2 times 20 times 5 the cos 5 pi plus I sin 5 pi, or you can write this is 45, 20 the 900 maybe. So this is 2 to the power 10 times, this will be minus 1 plus this will be I equal times 0. Yeah, I times 0. So 2 to the power 10 times minus 1 equal to minus 2 to the power 10. You can verify this value in your calculator as well. So in this way we can solve this question. Now move to problem number 3. The problem number 3 is just I square is given. Solution. Here we have given I square. This is also not in polar form, so let z equal to I only. That can be expressed as 0 plus I equal x plus iy. Therefore x equal to 0 and y equal to 1. Therefore r equal root under x square plus y square equal 1 is a 0 and 1. Tan theta equal y by x equal 1 by 0 is infinity. Therefore theta equal to 90 degree or pi by 2. Now z equal to, in polar form, 1 times cos 90 plus I sin 90 degree. I square, that means z square equal simply cos 90 plus I sin 90 whole square is that r is 1. Now using De-Moivre's theorem, using De-Moivre's theorem, you can express that is that r square 1 square is 1 itself, then cos 2 times 90 plus I sin 2 times 90 degree is cos 180 degree plus I sin 180 degree. Cos 180 degree is what? Minus 1 plus 0. Therefore I square equal to minus 1. It is also verified by this problem as well. So we have completed this.